Hey folks, let's talk about energy. What is it? If you really think about it, it might seem a little bit mysterious. So in this video, we're going to go through some basic definitions of energy, looking at random versus ordered energy, and there's an important distinction there. We're going to look at work and heat and how the two of those relate to each other and relate to energy. Then we're going to define what we call kinetic energy. What is that? And something that may be even stranger is potential energy. But what's important about the two of those is that they link together to form an important law of the universe, which is conservation of energy. And then at the end, we'll look at power. A lot of times we consider power, we use power and energy interchangeably, but there is an important distinction. And we'll talk about the difference between power and energy. All right, so let's just start by just using an example in nature of a busy bee. Um, and this is a carpenter bee that was at one point taking aim at a railing on our deck. And they're just known as really hard workers. You can see them working away, chewing away at the wood, putting a hole actually in the railing. It was pretty amazing to watch this process, but that's a lot of energy. And actually, bees consume a lot of energy. All right, so what is energy? Well, the first thing we're going to do is just look at the basic definition of energy as a capacity to do work. Okay, so that seems kind of nebulous. What does that mean? Well, work actually has a specific definition associated with it. It's an ordered form of energy because when you're doing work, you're generally doing something that moves or does something in a particular direction. It's very ordered. There's an ordered process to it. And in fact, there's an equation that we use to define work. So we define work as being equal to F, which is force, times distance. So we see these stormtroopers here actually in this little one's pushing the other in the wheelchair. And that's probably because when he was shooting at something, he couldn't hit it, because we know stormtroopers have horrible aim. And anyway, so that process is, so the stormtrooper that's pushing the wheelchair is applying a force, and that stormtrooper then is moving the wheelchair a certain distance. And the work required for that is the product of the force being applied times the distance. Okay, so that means we need to be concerned about units. So what are the units of work, this ordered form of energy? Well, if we go back to our previous discussions, we know that force has units of newtons, right? And 1 newton, if you recall, was equal to 1 kilogram meter per second squared. So that would be our SI unit, our International System of Units. That would be the definition there of the Newton. And then if we take that and we multiply it by distance, which again, the system, the unit we're going to use is going to be the meter. And so that means that what we're doing is we're taking a kilogram meter per second squared, and we're multiplying it by meters, and that gives us units of kilogram meter squared per second squared. Okay, so we have this set of units for work, kilogram meter squared per second squared, right? And this is going to be because, remember, we said that energy was the capacity to do work. That means these are the units corresponding to energy. And because energy is so important and pervasive in much of scientific research and scientific findings, that we actually have a name for that. Just like we called 1 kilogram meter per second squared for force, we named that the Newton. We're going to have a definition for a kilogram meter squared per second squared, And the specific unit for that is called the joule, named after James Joule, and given the symbol J. So that's going to be our standard unit for energy. It's called the joule, and it's equal to 1 kilogram meter squared per second squared. All right, so work is the ordered form. Now remember we said earlier that we have a situation where energy can be ordered and disordered. So what is disordered energy? Disordered energy is just very simply heat, okay? It's random, it's disordered, and when we think of heat, what does that mean? Well, what we're talking about here, for example, in this little example, is that we've got this container filled with molecules. Okay, so what we can see here is this shows a situation where we've got a bunch of molecules in a container, and you notice they're moving about randomly. But notice the temperature and what happens. And you're probably already aware of this. This would seem somewhat intuitive that a higher temperature very simply means more energy. And when we look at the motion within the situation, and I'm going to go back and do this again so we can see it. When we look at the motion within this, we can see that the molecules are moving about randomly. It's not ordered at all. And their energy, and in fact, you just look at the speed of motion, their speed of their motion really slows down as the temperature drops. So a higher temperature means more energy for the molecules, moving about with more speed within the sample, within this particular beaker, moving about with more speed. But again, it's random, it's not directed. The net result, for example, if, just go back again, if we had ordered form, if the molecules in this were ordered and all moving in the same direction, what would happen? Well, the container would move along with it. The container is not moving. The reason the container is not moving is because the molecules are moving about randomly in all directions. So the result is that the container remains stationary. So this is an example of what we call random energy, and we call that heat. All right, so we've got ordered energy, which is work, and random energy, which is heat, but then we also break down energy in terms of kinetic energy, which is the energy of motion. I mean, that's very simply, kinetic energy means motion. That's what we have here. We've got the energy of motion, and this is the definition of kinetic energy, Ke for kinetic energy, all right? And we sometimes give that the symbol T. So you will see me frequently write T because it's just easier to write. When you see that capital T, that means we're talking about kinetic energy, and that's equal to 1/2 mv squared, where m is the mass, and v is the velocity. Now you notice that, remember when we talked about velocity early on, that velocity was a vector quantity, had direction to it, and velocity could be plus or minus depending on direction. We've also got 3 dimensions of space. That's important as well. But here we're just talking about velocity squared. So direction doesn't matter in terms of kinetic energy. Kinetic energy does not have a direction to it. It has just a value. It's what we call a scalar quantity, not a vector quantity. But so we can calculate this. So again, if you look at this, an object in motion has kinetic energy. That kinetic energy is related to its mass. The higher the mass, the greater the energy. And it's related to its velocity. A higher velocity yields a greater kinetic energy. Again, all that should make sense, but that's the definition of kinetic energy. So let's check the units here. We've already said that we have these units of joules that we got from looking at the definition of work. What about kinetic energy? Is that consistent with that definition? Well, let's take a look here. So we've got mass, and that's kilograms, right? Mass corresponds to kilograms. And the units of velocity are meters per second, right? So meters per second, that's velocity. So when we square that, we get kilogram meters squared per second squared, which were the same units as work. And that, of course, again, is the definition of the joule. So the joule, again, shows up here in the kinetic energy relationship as our unit for energy. And that's what we'll be using in a standard way when we talk about energy. We're going to use the units of joules. This is related to, and this is a problem that we're going to be talking about later on, but related to the calorie. The calorie, which you no doubt heard about, and certainly we use the term calorie when we're talking about food and the energy content of food. The calorie is a unit of energy, but it's not the metric system unit of energy. And in fact, the calorie is defined in terms of the temperature, raising the temperature of 1 gram of water by 1 degree Celsius. And in fact, the relationship between the calorie, the standard calorie, and that's different from the food calorie, and I'm going to mention this in a few minutes, but 1 calorie is related to the joule. Oops, let's go back to that. 4.184 joules. So 1 calorie is 4.184 joules. And again, this is something you go into Wolfram Alpha, you could easily do this, show this in Wolfram Alpha. So that's a calorie. Now there's a difference between the standard calorie and what's called the food calorie. So when you look on the label of any kind of food stuff that you might be consuming, it's going to give you the calorie content per serving, whatever that serving is defined as. But in that case, what we actually have for food calories here is, and I'm going to erase, actually, I'm just going to write this up here at the top, that what we've got are here in the corner. So food calories are actually given a capital C. So there's capital C calories. And a food calorie is 1 kilocalorie. And a kilocalorie, all right, well, we're talking about those kinds of calories. That means it's equal to 1,000 little calories. All right, so then we talk about food calories. That's what we're talking about when we do that. And as I said, we're going to do a calculation associated with this in another situation here, but not in this video. There we have. So the standard unit for energy in the metric system, in the MKS system, in the so-called SI system, the international system, is the joule. And that's related to the calorie unit that probably you're much more familiar with in this way. All right, so that's kinetic energy. There's also this thing called potential energy, and it's the energy of interaction. All right, so it's an energy that's related to interaction. You can think of it as stored energy associated with energy. So that there are different types of potential energy, and it depends on the nature of the interaction that we're looking at. There's gravitational potential energy. We'll be doing some calculations associated with this. For gravitational potential energy, it would be if you were standing on top of a ledge and you jump. Before you jumped, you didn't have any kinetic energy, but you have potential energy based on the height of the ledge. And we're going to do a calculation associated with Gwen Stacy falling based on the height from which she falls. So stay tuned for that in another video. So that's gravitational, and that's an interaction. Gravity is a force, and there's an interaction between two bodies that create that. And so whenever you have an interaction, you have this stored energy. So again, standing on top of the ledge, the energy is essentially stored as potential energy and isn't activated until you fall. It's my dog scratching in the background there. So I'm going to pause here for a second. Okay, so then another type of interaction is a Coulombic interaction, and this is just simply the interaction between charged particles. For example, when you have a positively charged particle, and you know this, I'm sure, from high school science classes that you may have taken, that a positively charged particle and a negatively charged particle are attracted to each other. If we've got particles which have the same charge, they're repelled. Those are what are called Coulombic interactions, and there's a potential energy associated with those. That's really, really important in chemistry because most of chemistry is based on electrons and charged particles interacting and changes in the distribution of those particles in a chemical reaction. So there's potential energy stored in the interaction between charged particles. That's called Coulombic. All right. And as I mentioned, most chemistry is based on these Coulombic interactions. What holds molecules together are Coulombic interactions. When you have a chemical process, and we'll be doing some demonstrations of this that I will record and post, when you have a combustion reaction, for example, where energy is released in the form of fire, heat, that is a process that is due to the release of stored potential energy in the bonds within the molecules that leads to that release of energy. Okay, they're magnetic. Obviously, you've got electric. We know electromagnetism. There's a magnetic form. So they're magnetic interaction between the poles of a magnet. That's stored potential energy as well that can lead to kinetic energy. So there's nuclear potential energy, which is due to the nuclear attraction between the particles in the nucleus, the neutrons and protons, and quarks for that matter. This is a very strong interaction, and this is what leads to the powerful energy released in nuclear explosions, and in fact, the energy that is released in nuclear power plants that generate electricity. And now, if you go back and think about in the earlier video when we talked about the basic forces in nature, we talked about gravitational force, we talked about electromagnetic force, we talked about nuclear force. So they're all here. All these interactions have a particular potential associated with them. Okay, so this video is already over 17 minutes long, which is longer than I like for typical videos. So what I'm going to do is I'm going to stop here, and I am going to continue this discussion of potential energy in the next video. So stay tuned.